We're going to change the instructions from use a graphing calculator to without a graphing calculator. Graph y equals log 8 of x. So you might still be at the stage where off to the side you're thinking exponential graphs, y equals 8 to the x, and you know that it has the point 0, 1 and 1, 8 with an asymptote right there. But with our log graphs, we want to get to the place where you also just know what a log graph looks like. You know that your log graph always has the point 1, 0, because it's a inverse of 8 to the x. It makes sense. 8 to the x has 0, 1. A log graph will always have 1, 0. It will also have the point 8, 1, just because our inverse graph has 1, 8. So a log base 8 of x is going to have 8, 1. The other thing you can do is you can say, hey, if I plug in 8 for x, log 8 of 8 is asking 8 to what exponent would be 8? It would have to be 1. And so our final graph looks like this, and our asymptote, instead of being a horizontal asymptote, becomes a vertical asymptote at x equals 0. So what are the intercepts? Well, there's only an x-intercept, and it's equal to 1. Our equation of our asymptote is x equals 0. The domain is now x is bigger than 0, and our range is everything. Yes. How do we know that logs and exponentials are inverses of each other? That's why the log graph was, or the log equation was introduced. Like, how do you know that a square root and squaring are inverses of each other? You learned they do the opposite things. Yeah, just knowing that the log is the inverse. They undo each other's operations. So an exponential equation is putting something to a power. Undoing that power is doing a logarithmic graph. Just like squaring, you know what that does, and square rooting undoes that. The hard part now is you just haven't worked enough with logarithms to feel comfortable that you can say, oh, that undoes that. Right? Probably was, it's more abstract than a square root sign. But when you first learned square root signs, that was also weird for you. It's hard to think about that now. But when you first learned about a square root sign, you're like, ooh, this is a weird symbol that we have to draw. And what does this mean? And you had to be told over and over again what it meant. And now it seems like, oh, square root signs are common sense. Everybody should know what a square root sign is. Right? But go to your little cousin in grade 2 and say, hey, figure this out. Square root of 9. And they'll be like, what? Okay, so we are going to add some questions to this. I think you might have room on page 400. Is that true? Yes. Turn to page 400. We're going to do 2 more graphing questions. We're going to graph y equals 4 log base 3 of x plus 1 minus 5. Page 400 is a blank page. So now, how do we do a graphing of this where we have a bunch of transformations? You do it the same way that you would do all your transformations. You have to know what your parent function is and the key points on your parent function. So the first thing you have to be able to recognize out of this is that the parent function is log base 3 of x. And again, you want to be able to quickly sketch your base graph of a log with 2 points, 1 comma 0. That does not look like a 1 comma 0, and with a base 3 you'd have 3 comma 1. So we can quickly view our parent graph, and then we can look at the numbers that we have from left to right. What will this 4 do? Vertical or horizontal? Close. Vertical. And it will be stretch, compression, translation, stretch. You're going to multiply your y values by 4. The next number you run into is the 3. You have to make sure that you note that and say to yourself, hey, this 3 is part of my parent graph. It does not do anything transformations-wise. So that's one of the reasons that both exponential and logarithmic graphs, I didn't introduce them in the transformations unit because they have some extra numbers that can throw you off. But that 3 is part of your parent graph. The next number that we run into is the 1, and this is going to be horizontal translation 1 unit to the left. And finally, we have a vertical translation 5 units down. So we use our same strategies that we've used in transformations. You take your points. We have 3 comma 1 and 1 comma 0. And our asymptote at x equals 0. We do stretches and compressions first, then translations. So the only stretch we have is y by 4. So we'll have the point 3 comma 4 and still 1 comma 0. And then translations-wise, we've got 1 to the left and 5 down, 1 to the left, 5 down. And the last thing we have to think about is what is the only thing that's going to affect that vertical asymptote at x equals 0? Should the 3 be? Yes, the 3 should be a 2. 1 to the left. There we go. What is the only thing that's going to affect our vertical asymptote at x equals 0? Translation. Left and right. So it'll be x equals -1. What's that? If it was an exponential graph, then it would be the 5 that would move it, yes. And so now that we've got our new points and our new asymptote, we have enough information to sketch our graph. So I can start by labeling my asymptote at x equals -1. I have the point 2 comma 1. And I have the point, 2 comma -1. Man. There's it. It's 2 comma -1 and 0. And where your points are with respect to your asymptote will tell you which way this curve is going to grow. Can you tell that it's got to go and approach the asymptote this way? And curl. The same basic shape as your logarithmic graph needs to show up in your final graph. Is it an E error if your asymptote doesn't have errors? That is one that they do not take off an E error, but I like your asymptote does continue on forever, so I put arrowheads on my asymptote as well. Yes, so this has that similar shape. Yeah, it does increase forever. It just flattens out, but it does keep getting bigger and bigger and bigger. So there is no horizontal asymptote on a log graph. But as long as it's going through the 2 points that you indicated and you have the same shape, then you're going to be fine, right? Problematic shapes. If you drew a straight line here and then a straight line there and then a straight line down, then you would lose a mark for shape because it's not curved as it should be. All right, let's do one more, and then we'll do example 3 at the same time. Graph y equals 2 natural log. How complicated do you want? Oh, let's pull out everything. Let's do natural log. Let's have a fraction, right? Here we go. Everything combined. So first of all, you need to recognize the parent graph. What's the parent graph here? The parent graph would be the natural log of x. And it's going to have the point 1, 0, just like every log graph. And it's going to have the point e, 1. It still has an asymptote at x equals 0. E is 2.7-ish. Ooh, just thinking about that. 2.7-ish is really close to what it actually is because it's 2.7181, and then it's almost like another 8. I don't know. Yeah, I don't know. That last one was a fail. But the rest of it is kind of 2.718-ish. Yeah, you can for estimating it. What kind of transformations do we have? What's this 2? Kino? Horizontal or vertical? Diagonal. Close. Vertical stretch. You'll multiply y by 2. 1/2. Horizontal stretch, x by 2. What about this 2? Horizontal translation, how much? 4 to the left, of course. You have to factor. We didn't factor. Remember that special rule? That one that I said we should always have on your reminder at 10 p.m. every night? You have to write it in factored form. So I'm going to just shift this up so that, or we can just don't shift it up. Write it above there. Y equals 2 natural log. Factor out the 1/2. Sometimes when there's lots of brackets, I like to introduce different styles of brackets so you know where one bracket starts and one bracket ends. Why is it 4? The best way I find to know what number is going to go there is I say, well, 1/2 times that has to be 2. Then it becomes really obvious that it needs to be 4. And so it's a horizontal translation 4 to the left. And we didn't have to. By writing it above, we kind of saved ourselves from being too mad that we ran out of space. And then finally, we've got a vertical translation 3 down. So the fact that this one had a factoring makes it a little bit more complicated. The fact that the base is e seems like it's a little scarier, but it's not actually bad. Everything's still the same. we're starting with our points, e comma 1, 1 comma 0, and our asymptote at x equals 0. We do all of our stretches first, then our translations. Our stretches were y by 2 and x by 2. So y by 2, those ones are straightforward. And x by 2, this will be 2. What will we get for that first one? 5.4-ish, which we would write here, though, if we wanted to keep everything as 2e. That's right. If Donald Duck had another child, it probably would have been called 2e. Anyways. And then finally, we're going to go 4 to the left and 3 down. You don't think so? Huey, Louie, Tooey, Dewey? You fit right in. You don't remember? Well, their names were Huey, Louie, and Dewey. So Tooey seems like it fit right in there. 3 down, we'll do those ones first. You would get -1 and -3. 4 to the left, well, this one's easy. They'll become -2. And this one, 2e minus 4. So you do 2 times 2.7, which is 5.4, minus 4. 5.4 minus 4 is approximately 1.4. And that kind of mental math will help us draw it on our graph. What's going to happen to our asymptote? It's moved 4 to the left, so now it's at x equals -4. Putting this all together, we have our asymptote at x equals -4. We have our point. One of them, the easy one, at -2, -3. The not so easy one at 1.4, comma -1. And we'd still label it as 2e minus 4, comma -1. No, I don't think they would take off an error as labeling it as 1.4. And then based on those 2 points, drawing your curve towards your asymptote, arrowheads on the end of your graph, and this would be your final graph. So for question 2, the only real question is 7a. We are going to do example 3 right away because it's more graphing.